All right, then. Well, let's start. I'll start talking now and see how it goes. Okay. Share my screen. Always. So our topic of my today talk is a Python script that I developed while working on this idea of cloud optimizing HDF5 files. And the reason why is because I needed additional statistics or understanding of dataset settings in a given file. And there is a tool in HDF5 library called H5stat that one can run. For example, I run here. And let's say, for example, this is some file, and it'll give you a lot of information about various aspects of the file. I'm not going to go into details, what it means and everything else. But it turned out that what I was interested in about datasets in this file, it didn't hit. And so I developed this Python script to give me that information. For example, for datasets, it kind of has this kind of information here. And there are some for one-dimensional datasets again, a little bit more, but generally speaking, not what I was really interested in. So I wrote this script and I want to talk and show how it works. The script is available on GitHub as a gist, just sort of a piece of code. It's not in a repository. It is a kind of repository in GitHub, but not the real repository. And I update it from time to time, typically when I make some corrections, rare bug fixes, and some new statistics that I think could be helpful. And the name of this script, obviously, I called it appropriately H5stat extra, because it's extra information. And it takes a couple of command line options. So obviously, there has to be an HDF5 file given for which the statistics will be reported. And then depending what one wants, it can actually, the script can, instead of aggregate statistics that by default it gives, it can actually print out all the specific statistical information that's collected for each data set in the file. And also, it can do it in two formats. One is just a data set per line, very basic kind of plain text format, kind of good for grabbing those lines if you want to extract something particular. Also, you can get that same information as a JSON. So that JSON I targeted can be directly importable in something like pandas into a data frame. So those kind of two versions are possible. What I'm going to show here is mostly this aggregate information in terms of tables that this script can print out. And to get that, for example, for this same file that I used, I can write Python and then H5stat, and then I can say whatever I was saying. I forgot now. Let me pull this one out. Well, I'll probably remember. And what it will print out now, as you can see, this is this tabular kind of output. And this is a default look if the file is a typical HDF5 file. In other words, doesn't have any cloud optimization applied to it. So what is by default given? Basically, it says what the file is here. Sorry, wrong line, this one. Friendly warning that compact data sets are excluded from statistics. And the reason why is because the way how they're stored in the file doesn't really impact all the statistics reported here. So they're kind of like a separate storage method, and so they don't impact, they don't influence what I was interested in. And then it tells how many contiguous data sets are in the file and how many chunk chunk data sets are in the file here. And then everything else is printed in this ASCII table, or as a set of ASCII tables. For example, here, typically I'm looking at the sizes of contiguous data sets in the file, since there is 61 of them. And these are the various sizes in bytes, for example, where they fill in. And this particular file has all their contiguous data sets less than 1 megabyte. So this one, basically, this is the number of contiguous data sets. The next column is the percentage of each of this of data set in this category compared to the total number of contiguous data sets, and this is just the cumulative sum of the percentages given here, which I found it easier to sort of look at rather than calculate myself in, anytime I needed that information. So after the sizing, looking at the sizes of contiguous data sets, the next one is the chunk data sets and what are their chunk sizes in bytes. And again, here, for example, we can hear that there are 43 chunk data sets with chunk sizes in bytes between 10 and 1,000 bytes. This is the size uncompressed. This is just by the definition of the chunk shape. And so you can see by the time we reach between 10,000 and 100,000 bytes, we are close to 96% of all the chunk data sets in a file. And there are 10. This is an interesting point here. This is the interesting thing in this file. There are 10 chunk data sets where the chunk size is bigger than 16 megabytes. So these are pretty large chunks. Then I'm going through a very detailed table that looks at the ratio between the chunk shape to the shape of the data set. And the bins here are not regular. They're a little smaller, then get bigger, then they get bigger, because I was interested in various aspects of their extent ratios or shape ratios. So, but anyway, for this particular file, we see that most of these, all of these data sets are, for example, 10% or more. In other words, their chunk is 10% or more of data set shape. So they're pretty bigger chunks. And then the next table looks at how many chunks are actually stored for each chunk data set in the file. Because if the chunk doesn't have any data, the library is not going to store it in the file. So even if by the chunk shape, you would expect a lot more chunks to be in the file, if they don't have any data, they're not going to be in the file. So this is exactly how many chunks are actually in the file. And so here we see that we have 37 chunk data sets with one chunk in the file. And then everything else, because the cumulative sum is here 100, 207 chunk data sets have between 2 or 9 chunks in the file. And here I'm looking at the total stored size of chunk data sets. So this means all the chunks that are in the file and what are their actual sizes in bytes, how much of that. And as we can see, most of them are less than 1 megabyte. And there are 3 of them who are between 16 and 32 megabytes. In other words, these are now chunks that are compressed, and everything else that happened to them on their way to the file. So that total of their storage size is between 16 and 32 megabytes. And finally, I'm looking at the final table here, looks at the dataset chunk cache size. This is an interesting parameter for people who would like to read data from such a file. And here it says that if anyone uses just the default chunk cache size, which is 1 megabyte, essentially 96% of the datasets would fit into that chunk cache. And there are only 10, or about 4.1% of chunk data sets that really require chunk cache bigger even of 16 MB. Now, this table like this doesn't tell you what would that ideal size be. Obviously, I could increase the number of these rows in the table, but I was kind of happy with just knowing this kind of level of statistics. So this output that I just showed is for a typical HDF5 file. In case that this file or a given file is cloud optimized, which one cloud optimization technique uses a so-called paged aggregation file space strategy. I like to call them paged files. It's easier. So if that file is paged, then there is additional statistics that this script will report, and I can show you. Let me just clean this. So I think I have a version. I think I know I have. So this is now a version of this cloud optimized file. Version of previous file is cloud optimized. It is cloud optimized in the way that the file is now divided in 8 MB pages. And I've been talking about this for a while, but as they say on TV, if you joined us only now, quick catch up. Paged file means that when this file was created, the library was instructed to separate internal file metadata in separate pages from the data that's written to the file. And that separation basically makes significant reduction in the number of read requests for anything from this file, which is crucial parameter for cloud optimized files. And so this file was optimized by basically dividing it in pages of 8 MB. And there are 8 MB allocated for internal file metadata, as many pages as that requires. And there were 8 MB pages for the data, like chunks or contiguous data sets, as many pages as required. And that all goes into a single HDF5 file. And so with this file, oops, that's the wrong one. How was I able to do this? Okay, my mistake. We'll correct it quickly. No. So now we're going to get the correct stats. So now there are more pages, or tables, sorry, page. So here again, this is the command I use to run this script. And now we have a text. Obviously, now there is more information. Beyond how many data sets are in the file, there is now this line that says that this file is now using this paged file strategy. And it reports how many bytes were per page. So I made a mistake. It wasn't 8 MB, it was 8 MB. My bad. So 8,000 bytes per page. And then the tables that are here, these are the same ones as before, so I'm not going to talk about them. So here, this is the chunk cache size. We covered that one. Everything below now happens only if the file is this paged file. And so what we count here is how many chunk data sets are actually outside of this file page. So this was something interesting that that's why this file is so, that's why I chose this file. If you remember in the previous cases when I talked about chunk sizes, let me find here, remember that there were chunk size in bytes. Where was that one? Oh yes, here. Chunk size in bytes here, there were 10 chunk data sets whose chunk size by definition was bigger than 16 megabytes. Well, probably some of these chunks could not have been made smaller than 8 megabytes, the page size, after compression and everything. And so they just ended up being too big. And so the library, when creating this paged file, had to store them outside of the pages. And that's what this table that is trying to basically shows here. So it says that essentially 3 chunk data sets ended up being outside. Some of their chunks, not all of them, but some of their chunks ended up being outside of the file pages completely. So they are like this kind of blobs of bytes inside of this file that are not belonging to any file page. All the else chunk data sets were inside the file pages. And everything that follows next in these tables, we're going to exclude these 3 data sets because they are now outside of the file pages. And so they're going to, one way or another, introduce, sort of ruin the statistics, if you will. They're not anymore really subject of the following statistics that is displayed in these pages. And so here we see how many pages hold each chunk data set. And we can see that almost 93%, 94% of all the chunk data sets are all within one file page, which is a fairly good sign. It means that the library, at least when it reads this file and goes for data from any data for all of these data sets, it's going to make just one read, bring that page where that data set is, and gets all its data. The next one's looking at this kind of page anomaly, which means that compared to the stored chunk dataset size, is this chunk dataset in more pages than really would need? So in other words, even if I have a chunk that could fit into a single page, for whatever the reason, all its chunks have not ended up in the single page. And so this is what the statistics reports, and it says that basically we'll have essentially either 1 or 2 pages per each chunk dataset, which is not bad. This is, again, counting of only chunk datasets that fit the file page. And finally, there is another one. It's kind of version of the previous one, but this gives just statistics of a page percent. Well, this is really more aggregation of aggregation. So basically, looking at these pages, it gives me and finds the page with the most chunks of one dataset in it, and then looks at what is the percentage of all these chunks in a single page compared to all the chunk data. I think I explained it correctly, but when you see the formula, it makes more sense. In other words, it basically says that 13 chunk datasets have somewhere between 40 and 60% of their chunks in a single page. That's what it basically, how to interpret it. And this is all that you get so far regarding this extra dataset statistics. It works also for the HDF5 files in S3 store, either Amazon S3 store or any S3 compatible object store. It supports S3 URI, so basically, oops, my bad. Let me see. Well, I can do this maybe. I think I'm pretty. Yes. So, for example, for let's see. Yes. So, for example, for this file, it can go straight to the S3 wherever it is and gives you the example. So, I'm going to show you how it works now. It takes a little bit more time because it goes now from my laptop to S3 to fetch the data, and eventually there you go. So now this is the statistics for that file. And that's basically, oh yeah, I didn't show the other forms of output. So if I want to, as I said, if I want to give, let's say, this textual, not tabular, but more specific information for each dataset, you use the show command line options, and what you get is this kind of output here. That I talked about. It's a plain text, one dataset per line. It doesn't look nice, but you can grep, and I think you can read. There's a space, the limited information. If this is, if I use JSON, let me then use this because maybe it's more nicer output. Yes, so now we have it here, which doesn't help improve its looks, but we can always, I think, say format document. There you go. And now it looks much nicer. Obviously, there's a lot of information, but as you can see, there's a data set here, how many chunks stored, chunk size in bytes, how many bytes is actually total stored. And here's the size, minimum chunk size in bytes, the maximum chunk size, this ratio between the chunk shape and the dataset shape, and file page. There's a sixth file page in the file, and all of them are in that page. So that's basically all the information that this script can give. That's out of. So this is the information that is used to produce all these tables, to put it simply. And with that, I am done.
All right, thanks, Alexander.
You are welcome.
And we can post a link to where you have that stored in the description.
I think you have it. You actually have it in that announcement.
I do have it. I was talking to people in the future who will listen to this recording.
Ah,
yeah.
My experience in making these videos.
So next week we'll have Scott on Call the Doctor. So we'll see everyone then. Thank you.
All right. Take care.